Hey everybody, welcome to today's Astronomy on Tap. We're super excited to have you here. Thanks for bearing with us as we get everything up and running on the YouTube live stream. And we'll get started now. So I'm going to be one of your hosts today. I'll be emceeing along with Isabella. And so I'm Pratik, and I'm a third-year astronomy graduate student at UC Davis.
Hi everyone, I'm Isabella and I'm a graduate student at UCLA.
So just to briefly go over what Astronomy on Tap is in case you haven't been to one of these before. It's basically a worldwide astronomy themed outreach effort that has a number of different branches in different cities in America, in Europe, and other parts of the world as well. And the whole idea is to just get people together in pre-pandemic times, usually at some kind of bar or brewery, and now online, and present them with various astronomy related talks given by both professional astronomers as well as amateur enthusiasts. This is the list of everything we'll be going over today. We're going to have two really cool talks, both of them by grad students at the University of California. And then afterwards, at the end, we'll also have a brief presentation on some super exciting recent astronomy news, as well as a trivia contest at the end.
Yeah, so if you all stick with us through the end and join us for trivia, you can win some of these fabulous prizes in a raffle. We have some fun stuff from Science Socks, which is Perseverance themed, and then we have some things from the Arecibo Observatory shop as well, so get excited. All right, so our first talk is by Lizvet and Dakota. So Lizvet earned her master's degree in aerospace engineering before she joined the astronomy department as a grad student at UCLA. And she is investigating the way we measure black hole masses across cosmic time, specifically modeling the regions around black holes at the centers of galaxies. Dakota is also a first-year graduate student at UCLA, and he's interested in exoplanet demographics and atmospheres, and he's currently studying the mechanisms that contribute to the evolution of planetary atmospheres. So Lizvet and Dakota, whenever you're ready, take it away.
And just bear with us for a second as we switch to their slides.
Sorry, slight technical difficulties there.
All right.
We're going though? Okay,
Everybody see this and hear us and everything? We're good?
cool.
All right. So I'm Dakota Tyler, first year grad student. I study exoplanets at UCLA, and I actually study exoplanets. Lizbeth, she took time out of her busy schedule to master my field and help me with this presentation.
Totally did not master it, but thanks, Dakota. My name is Elizabeth Villafaña.
Sorry, there's a cat as well.
Yeah, that's my kitten. Sorry. So anyways, continue on. We're going to talk about some exoplanets. They're pretty cool. So we actually found our first one in 1992. One that got more popularity was in 1995, but it's a more recent topic within astronomy. And it's pretty cool. We now have learned about more than 4,000 exoplanets, and NASA has a lot of information on it. So you can go ahead if you ever are curious. They have a lot of information about all the planets. But the main question is, how do we find them, right? And one of the first ways that we find them is through something called direct imaging.
Right. So in direct imaging, it is literally directly taking a picture of the planet. So you look up at some star somewhere that's situated in such a way that the planets are orbiting around it like this with respect to us. And you just take a picture of it. And the way that you can kind of think of it is when you look up into the night sky and you see some planets, Saturn, for example. The reason that we can see it is not because Saturn is emitting any light, but rather the sunlight is bouncing off of Saturn. And the reason you don't see Saturn during the day is because that sunlight being bounced off Saturn is getting drowned out by the sun. So when we directly image a planet, you take a coronagraph, which you can see right here on this video, which is just a black circle that goes over the sun or over the star, blocks out the starlight, and then allows us to image the planets. So this is a really cool video that's taken over almost a decade by Jason Wang and Kristen Murad that shows, yeah, like this is 4 different planets very, very far away orbiting a star.
But this method is also not that common, right?
Yeah, it's not the most prevalent way to find exoplanets for sure.
Okay.
One of the ways that is a lot more common though is the radial velocity method. So this is an indirect way of detecting planets. Where direct imaging, you're actually looking at the planet, snapping a picture. With the radial velocity method, you never actually see the planet. But if you look at the bottom of this video here, you can see that this spectrum, this rainbow looking feature at the bottom, kind of shifts from left to right. And that shift corresponds with the star moving, because when planets orbit stars, the planet just doesn't orbit. The star actually does its own small orbit around some common center of mass. And if you look at it with a precise enough instrument, you can detect that shift and infer that a planet is there orbiting. Now, the most common way, or the way that I'm most familiar with and the way that I use in my research, is the transit method. And this one is actually pretty simple. You stare at the star. Every once in a while, you'll get a dip in the brightness of the star, and then it'll return to its normal brightness. And again, this is not a direct way of detecting a planet, but indirectly you can infer, oh, you know, every 10 days, there's this periodic dip that's exactly the same size. It comes every 10 days, like without a doubt. And you can infer that there must be a planet that's blocking out a piece of that starlight.
So as I mentioned, we have already found like over 4,000 planets. So what exactly have we found? This is a plot showing the demographics of the planets we have found. On the x-axis, you have how long it takes to orbit its star, and on the y, you have its mass, right? So if you look at that like those green points, those are what we refer to as hot Jupiters. And that's because they are very close to their star. You can see they're between 1 to 10 days. They take 1 to 10 days to orbit their star and are about the size of Jupiter or even larger. When we first discovered those, or by we, I mean exoplanet researchers, when they first discovered those, it was kind of a shock, because when you learn about like planetary system formation, right? We used to believe that Jupiters would form where like our Jupiter's at. And then we just found a lot of these big planets really close to their host star. And then what we also found too was these, what we call super Earths and sub-Neptunes. As you can see, they're slightly more massive than Earth and a little less massive than Neptune, right? And Dakota can go ahead and talk a bit more about this particular like trend that we're seeing.
Yeah, so this next plot is going to blow up what I have circled here in this pink bubble. So these are super Earths and sub-Neptunes, and observers find that they're actually the most common planets around. So if you're a star, the most likely type of planet that you have is this super Earth or sub-Neptune sized planet. And that's interesting because we actually don't have any of those in our own solar system. Now, what you can see is that there's not only a lump of kind of super Earth / sub-Neptunes, but there's actually like a clear distinction between the sub-Neptunes and the super Earths. And when we think about what that means, it basically means that not only are these the most common planets that form, and there's some sort of mechanism that goes into forming planets of this size, but there's this radius valley in between the two. So there's a clear distinction between a sub-Neptune and a super Earth, and there's not really any planets sized right there in between. And that's it's not obvious. It's not intuitive as to why there would be some nonlinear distribution of planet sizes. And these are like some of the demographics questions that I'm interested in answering in my research, and that are kind of at the forefront of exoplanets as a whole. Now, before we get into the like really cool systems that have been found, we want to kind of like throw out a word of warning or caution. so that you don't get psyched, right? Like in life, you never want to get like psyched, like psyched out. You think one thing, and then like, no, that's not actually what's really going on at all.
So we just kind of want to tell you about some of these terms that exoplanet astronomers use really often.
Yeah. So I'll give you an example. Astronomers are almost notoriously uncreative with their names about things. Like
a bunch of letters.
Right.
Sometimes.
We'll just name something straight up. Like if this thing is big, we'll just call it like a big thing or whatever. And a good example is this really big telescope that's being built. It's a European telescope, and it is like an extremely large telescope. It's in the plans right now, like in the works being made. And of course, like aptly, it is named the EELT, the European Extremely Large Telescope. Like there's no caveats, there's nothing no trickery, like no funny business going on.
And then with black holes, they were theoretical for a very long time, predicted by Einstein, right, with his theory of general relativity. We thought they would exist. There was some kind of confirmation along the way. And more recently, 2 years ago, we have found the first image of a black hole, right, with a lot of collaborators. And it literally is a black hole. So sometimes, most of the time, astronomers are really upfront with their terminology choices. But Dakota wanted to help us out with the exoplanet terms here.
So in exoplanets, that's not always the case, right? Like you'll hear this term Earth-like a lot, right? And we all live on Earth. You know what Earth is like, right?
So you think it's like Earth.
It's like Earth. But I will just be the one to tell you that most of the planets that we say are Earth-like are like not really like Earth. You may hear Earth-like and be thinking, oh, like what kind of birds does this planet have? Or what kind of whales swim in the ocean? But really what we mean by Earth-like is that it's basically small. It's small and rocky. So Mercury is an Earth-like planet. Mars is an Earth-like planet. Venus is an Earth-like planet. And there are no birds and no whales on any of these planets. And
it's more kind of like a guideline. Like it's just like within this mass range, within this radius range. If you're within like this Earth-like regime, it's an Earth-like planet.
Right. And we don't want to fool anybody when we start talking about cool Earth-like stuff later on. And so another one is the habitable zone. You'll hear this a lot too, an Earth-like planet in the habitable zone. So this is Goldilocks.
It's commonly called the Goldilocks zone. You may have heard of that before. So.
Yeah. So Goldilocks, for those of you who don't know, I don't know, I'm a bit older than everybody else. So
Goldilocks and the Three Bears is known.
Yeah. Okay, so Goldilocks is this little girl. She's like prancing through the woods. She thinks she owns the place, frankly. She breaks into this poor family of bears' house.
Oh, I never thought of it that way.
And really just starts like making a mess of the place. So she's sleeping in the bed. She's putting her feet on the furniture.
Trying their food.
Right? She's eating their food, their porridge at that, which I don't even know what porridge is.
Is it like oatmeal? I don't know.
Some sort of lumpy soup, right?
But anyways.
So she's eating their porridge, and she's being really bougie about it. Like she's eating their food, and she's judging like whether or not it was prepared properly or like seasoned correctly. And in this case, water is kind of like Goldilocks. Like water is this weird bougie liquid that's only gonna be a liquid.
Like Voss water?
Like Voss water, yeah. It's like
Smart
this
water, Fiji water?
It's this bougie liquid that's only gonna be a liquid in certain circumstances. Right? So if the water is on a planet that's too close, it's not going to be a liquid. Like it's, water doesn't deal with the hotness. I'm not a big fan of, things that are too hot either. But the water will just evaporate away, maybe be like lost into space.
Like hot Jupiters. You can't have water there.
You can't have any water. It's way too close, way too hot. Right? And likewise, if it's too far away, the water also cannot be a liquid. It'll freeze into an ice, which is useless for life, at least as we know it.
And it's like, that's like what we call the frost line, and anything like Saturn, Jupiter are beyond this line. They're too cold. And then there's like where we're at, where it's just right.
Right. And this is also still like a super rough guideline because there's a lot of different things that go into a planet's atmosphere or like plate tectonics, things like that. They can alter the composition and make it possible or impossible for water to exist. And that is still a very different question about like habitability for life. Like we're really just talking about water here.
So we kind of just want to like make it clear that the habitable zone is like where water could form, but it doesn't necessarily mean that like the planet itself is habitable. Like you can think of Mars, for example. Mars is in the habitable zone, right? No. Venus
Yes.
is.
I think they both like pretty much are. Like they're both really close, but water can neither exist as a liquid on either.
So all these planets we know are in the habitable zone. They are just in this region where water could form. And so now I wanted to like share my favorite system as a non-exoplanet researcher. I remember the TRAPPIST-1 system really well, and I think I personally think it's the one that's known the most. It made a lot of like headlines. It was first first announced in 2016, and it was actually discovered in 2015 using the TRAPPIST telescope in Chile. And so the thing about it was that it was like a big announcement that these planets had been found, right? Originally, only 3 were found, and there was only 3 were found. And what happened after that was that then they used Spitzer. It's now retired, but there's a space telescope called Spitzer, and it focused on the system. And it spent like over 21 days of just observing the system straight. And it confirmed the first 2 planets and then found that the 3rd planet was actually 3 planets and found another one, making these planets, the way that the exoplanets are called is that it first usually takes the name of its star. In this case, it's TRAPPIST, the telescope that was used. And the first planet around the star gets the name B. So there's these 7 Earth-like planets. And as we mentioned, that just means that they all have the size and like the radius and mass that's close to Earth-like. And that's what makes it really exciting. It's it's the system that we have found with the most Earth-like planets, and it has 7 of them. What's also interesting about them is that they all take less than 20 days to orbit their star. They all lie within 1/5 of Mercury's orbit, like compared to our own solar system. And the reason they're able to be this close to their star and still be considered habitable is because the star that it orbits, it's about, I didn't mention that part, I totally forgot. It's about 40 light years away. So that means it takes like 40 years to get to us. And it's in the region of the sky near the constellation of Aquarius. And so it's actually it's called a red dwarf star, and these stars, they are much bigger, so much smaller. This star is about the size of Jupiter, and it burns a lot slower, so it's a lot cooler. So these planets can be a lot closer to the star. And the first 3 planets within the system, it is believed, hypothesized that it would be too hot for water to exist, but the next 3 planets are considered to be in the habitable zone. And as we mentioned, that just means that water could form there in some sort of form. And it's been like one of the systems that has been most studied just because it has the most rocky planets. In our solar system, we only have Venus, Earth, and Mars that are rocky planets, terrestrial planets. So it was just really exciting, I guess, for astronomers to find 7 in one, and realizing that our solar system might not really be what's like average. It's just so diverse out there. And then this last one is kind of just an artist's like depiction of what it would look like on the surface of one of these planets if there was a surface. What's cool about it is just that it's showing that you would be able to see other planets there because they would appear about the size of our moon just because of how close all these planets are to each other. And what also is cool about this system is the idea that interplanetary travel would only take a few days compared to the years it takes in our solar system. And also the sky would be like red-orange all the time. And I forgot to mention, which I wanted to mention, is that it is believed they're probably tidally locked. So tidally locked is just like a fancy word to say that the same side always faces the star. So like our moon is tidally locked to Earth. So all these planets, it's hypothesized that they would always be nighttime on one side and always be daytime on one side. So it's interesting because we are very excited that some are in the habitable zone, but if you have always nighttime, always daytime, how could like life survive there? Well, if it had an atmosphere, like a really thick atmosphere, then it would be able to have temperatures for water and spread out the warmth, right? The only thing is that it's very hard to detect like exoplanet atmospheres, and we don't know anything about their atmospheres. We just only know right now their densities, and it's the most precise measurements we have of any other like system. As for the atmosphere stuff, I'll let Dakota take over that soon, since that's actually what he's researching. But this is, to me, in my personal opinion, one of the most popular systems. And recently they've come out with more papers, and they're just trying to figure out more about it because there's 7 Earth-like planets.
Do you have a favorite planet in the system?
No, but I'm gonna go with C.
C?
C's always the right answer, right?
I think so.
I think that's what I was told growing up.
Okay.
C.
All right. So I'm going to talk a little bit about a planet that I study in particular, but before that, we wanted to highlight some other really interesting candidates of exoplanets that have been found.
There's the one that I guess I wanted to highlight was the closest exoplanet to us, just because it's orbiting the closest star system to us. It's a triple system, Proxima Centauri. So Proxima Centauri B is the planet that orbits it, and it's about a few light years away. I'm gonna go with
Did
that.
you just calculate that in your head?
Yeah.
All right, that's pretty impressive.
Orders of magnitude. Okay, and then so there's another one too. That's Kepler 16b. That was the first planet we found that orbits a binary system. So you would get this cool like double star sunset like you get on Star Wars. So we wanted to put that out there for Star Wars fans.
Yeah. And admittedly, neither of us did our homework, and neither of us has actually seen Star Wars, which is heresy as an astronomer. But I think the planet that Elizabeth is referring to is called like Tatooine.
Putting us on blast. Okay.
Right. But yeah, I mean, that would be cool if you had a planet and that had 2 suns.
And what Dakota like brought up as we were doing this research is like pretty cool. There's more binary systems are more common in like than normal single star systems. So it's just probably more common to find planets with multiple star systems where they would have multiple stars in their sunset and sunrise.
Yeah, I think that most of the stars that you look up and see in the nighttime are really part of a binary star system that you just can't resolve because they're a little bit too far away. So the last interesting one that we wanted to talk about was TOI 849b. So this is a really interesting planet to me because it kind of falls right into the region of interesting exoplanet demographics that I like to study. So what they basically found was this planet, this kind of core of a planet that's orbiting super close to its star. And we believe that the entire atmosphere got blasted away, right? So you imagine taking like a Jupiter-sized planet, putting it right next to the star, and then the entire atmosphere just gets blasted away. And then what's left is a small core, right? So astronomers on planet Andromeda or whatever, like a billion years ago, may have looked at TOI 849b, which I'm quite sure they named it something better, and saw like an actual planet that was going through atmospheric escape, and like pieces of the atmosphere were getting blown away or whatever. But now when we look, all we see is this kind of remnant core. So that actually leads into what I study right now. So the planet that I'm studying is called WASP 69b. And this is a Saturn mass, but Jupiter-sized planet, right? So Jupiter is bigger than Saturn and more massive. But this is a planet of Saturn's mass that is kind of puffed up to the size of Jupiter. So it's a lower density. And this happens because you take some gas, you put it next to something hot like a star, and it expands. This is like thermodynamics, right?
Oh yeah, PV equals nRT.
PV equals nRT.
Yeah. T goes up, V goes up.
V goes up, the volume goes up, it expands, right? So in our observations of this planet, we can detect pieces of the atmosphere actually getting blown away. And that's really interesting because we're kind of analyzing this atmospheric mass loss in real time, right? We're looking at the process of, say, for example, TOI 849b, that is just this now core with no atmosphere. And we are studying the process that got it there, right? Like the evolutionary mechanism that led to what we observe now. And that is like really important for figuring out, you know, how these processes shape all planets. So one of the super interesting things about this WASP-69b planet is that it has a comet-like tail, which you can see here in this animation. This is some other animation, but it applies to WASP-69.
A planet has to be really close for a tail to happen like that, right? To its star.
I mean, I guess so. There's not a lot of I don't know of actually any other examples that have this, but there's plenty of other stars that are about that distance.
I was just thinking like a comet tail, right? Like we don't see that happening in our solar system, right? Oh, well, Mercury doesn't have an atmosphere, right? You told me that.
Yeah, Mercury doesn't really have much of an atmosphere.
So we couldn't see that with Mercury.
Right. But that makes sense though, right? It's a smaller planet, so it must have had a smaller atmosphere to begin with, which means it very quickly got blasted
but a
away
gas giant can keep it.
A gas giant has tons of atmosphere, right? And some of them, like in a hot Jupiter, maybe it has so much atmosphere that it'll never actually lose it all. But planets that are slightly smaller that have like a lot of atmosphere, but not too much, you know, they'll lose it. And at any rate, the hot Jupiter WASP-69b is losing its atmosphere. And as the planet orbits around the star, it like drags that kind of lost atmosphere around and forms this comet-like tail, which is like a really cool thing. It's very cool to me to imagine that. Like, that's just an amazing thing.
Like every astronomer with their research baby, you know?
Yeah.
So I think that actually concludes what we have. Unfortunately, I wanted to go way more into more cool exoplanets. There was so many, apparently some that they like hypothesized to have lava and all this other stuff. But unfortunately, for the sake of time, we couldn't go into that. But did want to encourage you to continue looking for your own search of exoplanets. Join Dakota in the search and figuring out what they're about. And NASA has a lot of pages, but we can go ahead and take questions. If there's any right now, let me see. Okay, let's see. We're getting questions. So one of them is, in the transit method of detection, why does the brightness drop when the planet orbits behind the star?
Okay, that's a really good question.
Should we go back to that slide?
Yeah, sure.
Give everyone that.
And I really glossed over it. Actually, I didn't even gloss over it. I don't think I said anything about it.
Yeah, it's right here. So there's that little dip right there.
Right. So the first dip is, it makes a lot of sense, right? And then you'll notice that as the planet circles around and starts going behind the star, the brightness actually increases slightly, right before that dip. And that's because as the planet starts to orbit behind the star with respect to us, it's now reflecting some of that starlight, right? So we not only have the brightness from the star, but we also have this additional brightness being reflected due to the planet's atmosphere. And you can do some spectroscopy on the atmosphere there and try to see what type of emission features are going on and get like a temperature of that planet's atmosphere.
They also asked, that same person asked, in that transit video, how is the small orbiting object able to decrease the brightness of the star so much?
Yeah, so I also think that this is like very exaggerated, just so it can make sense.
I've seen his plots; they're literally like a little drastic.
Yeah, to see the dip, yeah, you have to like zoom way in to like a tiny percent of the actual flux. But great question, yeah, like this is
exactly
a bit misleading.
And then there's also, apart from the size of planets, are there differences in composition? Super Earths are rocky, sub-Neptunes are gaseous. I guess they're asking about this part.
Yeah, so first of all, we don't know a ton about them, but that does make a little bit of sense, right?
All that, like, so right now, since as we mentioned, it's a little difficult to like actually analyze the atmosphere of a planet. So what astronomers can do is they can determine a planet's mass, planet size, and from that get a density, and based off the density try to like figure out what it's composed of, right? That's the understanding of it. And then
but that is the idea, right? Like once the cores kind of get to a certain size, they start attracting more atmosphere, and it makes total sense that we'd expect that the sub-Neptunes be having quite a bit much more of their mass in the form of atmosphere.
And then I'm sure that exoplanet astronomers are also very excited with JWST, right? Just because, as like, to answer the question about composition, we're hoping that with the launch of that telescope, that we'll be able to see more into exoplanets than we have before, right? Did I miss any questions? You see this one? Are there any thick, dense atmosphere terrestrial planets like Venus that have even larger amount? Okay, so I guess that's kind of answered by we don't know as much about atmospheres right now. That's kind of on the forefront of exoplanet research.
So the reason why it's kind of interesting to study these hot Jupiters right now and their atmospheres is because it's easier. The atmosphere is poofier and absorbing more photons. And so it makes it, like with our, instrumental limitations, easier to study with something that we can resolve on that level. Whereas the atmosphere of a Venus, for example, as thick as it is, that we know that Venus atmosphere is, it's very paper thin, and it's like really pushing up on the limits, if not beyond the limits of what we can actually detect with our spectrometers.
Yeah, we totally forgot to bring that up, that there's a lot of bias that goes into what we have found. That we, like how Dakota just mentioned, that we can detect certain things easier. So we just hope, like, moving forward with exoplanet research, right, that we'll be able to hopefully detect more in between, or maybe this is just how it is out there.
Yeah,
we don't know. That's the cool part about research.
With better instruments, better technology, we would hope to be able to detect more sensitive areas.
And then the last question we have is there a public project Zooniverse like for searching for exoplanet? What's Zooniverse?
Like online? I'm assuming this means like online, like Zoomiverse.
Oh, okay. NASA has a lot of good stuff.
Yeah, they have a kind of like a catalog. Yeah, Katie says citizen science projects. Yeah, I'm not actually aware personally of any specific
citizen science projects.
Okay, so yeah, that sounds like a good one. A lot of the planets that we looked at for this presentation were actually from NASA's exoplanet catalog. They made really cool animations for all these planets to simulate, whatever star system that they were in.
And they also have like a catalog that literally lists all over 4,000, and they like update it regularly as well, which is like pretty cool too.
Yeah.
Okay.
So yeah, thanks. It was fun. I hope that everybody learned something about exoplanets. Lizbeth taught me a lot. That's for sure.
Wait, one more. Using spectroscopic shift, how can you suss out how many planets there are and differentiate them? That would be radial velocity, right?
Okay, I think right. So the examples that we showed
were for one planet only.
Were for one planet, right? And you kind of get this very clear wobble from a star due to one planet. And you actually get that same relative wobble for each additional planet in the system. So if the question is, how can you suss out how many planets? I mean, if you're good and you have enough data and you can model it, I'm pretty sure that you can.
It's a lot of modeling.
Yeah, you can do like a lot of modeling and use there are different analysis tools like periodograms where you can pull out any periodic shifts that the star has for whatever reason.
And with the transit one, multiple planets show up as multiple dips, right? Yeah, correct. Okay.
Yeah. And but yeah, like using the spectroscopic shift, like that's like how you do it. That is exactly how you do it.
Cool. Well, I hope you all really enjoyed this presentation, learned about some cool exoplanets, and may your search continue. And hopefully you also want to take a class like I do now.
All right. Thanks, everybody.
Thank you. Bye. Good night.
Thank you so much, Dakota and Katie. That was an absolutely kick-ass talk. And it was really cool that you guys set up this like conversation style talk with both of you. So thanks again for speaking for us. We're gonna resume now with our second talk for today, and Isabella is going to introduce our second speaker.
So Katie is up next. Katie is a physics PhD candidate at UC Irvine. Her scientific interests are in galaxy evolution. She studies how satellite galaxies evolve and what they can tell us about the universe. She's an NSF Graduate Research Fellow and a member of the Board of Directors for the Astronomical Society of the Pacific. So Katie will get your slides up now.
Okay, is that all good? Can you see me and hear me? I think so. Okay, awesome. So thank you so much to all of the organizers for inviting me. It's really an honor to be here. And for all of y'all in U2 land, thanks for joining me. I'm really excited to talk to y'all about galaxies. So before I get going, I wanted to just take a second. So everyone picture a galaxy. What do you think a galaxy looks like? How big is it? What colors are involved? What kind of shape it is? So just take a second to do that. And does your galaxy look anything like that? So this is kind of a very common galaxy. It's a star-forming galaxy. This is the southern pinwheel galaxy. So this is something that you would see in the southern hemisphere. But it's kind of typical. You have like these spirals. There's a bunch of bright, blotchy kind of cloud things. And in all of those clouds, there's stars currently forming. So literally as this picture was taken, it is capturing stars being born. There's probably planets in this galaxy, like Dakota and Lizbeth were talking about. So this is our very typical galaxy. And something that y'all probably know is that there is just this huge, diverse, population of galaxies out in the universe. And one of my favorite things about galaxies is that we really had no idea that there was so many of these until just about 100 years ago. And actually, well, much earlier than that, only about 100 years ago did we decide that galaxies were a thing. So in the early mid-1920s, Edwin Hubble was studying a type of star called a variable star, or a Cepheid variable star. These stars literally change brightness as you stare at them in the night sky. If you look long enough, you'll see it get dimmer and brighter as you go through the night. And what he realized through studying these stars is that the Milky Way, that big swath of stars that you can see in the night sky at a really dark night, is actually its own galaxy. It's not the entire universe. Literally up until the 1920s, we thought the Milky Way was the entire universe. And then we realized that not only is the Milky Way just one of many, every little spot in the night sky has just almost countless galaxies. So this is one of my favorite images. It is the Hubble Ultra Deep Field. So this picture is from 2014, but just prior to that, the Hubble Space Telescope the director decided to take some of his time that he had to use the telescope and just look at a patch of sky that we thought was completely empty. We see it's just a completely dark, tiny little patch of sky. And he pointed the telescope and just stared at that spot for a while. And this is the kind of picture that we get back. Every single dot, every single blob and little spherical thing, swirly thing that you see in this picture is a galaxy. There's almost countless galaxies. Every spot of the night sky looks like this if you stare long enough. And so you can see there's just this diverse, really interesting population of galaxies out in the universe. And there's also a big population or a relatively large population of diverse galaxies very nearby to us, the Milky Way satellites. So two of the most famous satellites are the Large and Small Magellanic Clouds. So if you've ever had the privilege to look up at the night sky from the southern hemisphere on a dark, clear night, you've probably seen these two splotchy blobs. These are actually the Milky Way's largest satellites. So they're galaxies that are nearby us. And I'll get into kind of the definition of a satellite in a minute. But one of my favorite things about these two galaxies is that even though we only decided they were galaxies, like we as in astronomers decided they were galaxies, 100-ish years ago, they have been part of human culture since the advent of culture. There are just endless stories from indigenous cultures in the Southern Hemisphere that use the small and large Magellanic Clouds in their folklore and in their storytelling as ways to teach each other about, culture and humanity. So these are just two of ours. We have about 40 to 50 smaller galaxies around the Milky Way. So I have kind of a timeline of our discovery. We've known about the large and small Magellanic Clouds for years, but we decided they were galaxies in the 1920s. And as you can see, as we go through the 1900s, which is very weird to say, all of these blue dots that are popping up, these are all what we call the classical satellite galaxies. So they're definitely smaller than the Milky Way, but they're, dwarf galaxies. They're small, but they're not tiny. Those red and green dots that you see, I'll play that one more time. These are all the ultra faint dwarf galaxies. So these are the tiniest galaxies you've ever seen. And if you can tell in the video, there's this long time that goes by after we kind of find all of these one-off larger galaxies around us. And then there's this explosion of red and green dots. And that's because of technological advances. So in about 2005, with the Sloan Digital Sky Survey, we were able to just observe huge swaths of the night sky digitally and kind of go through all of the data using different like machine learning techniques and big data techniques, and find almost triple the amount of satellite galaxies that we knew around the Milky Way. So just to give you, since I've said satellite galaxies umpteen times already, I figured I should probably pin down what the definition is for y'all. So we believe that every single galaxy lives within a sphere of dark matter, or a dark matter halo. So you can literally think of a ball of dark matter with a little tiny galaxy, well, a galaxy in the center of it. So a smaller galaxy has a smaller halo, a larger galaxy has a larger halo. They kind of grow, we believe, one-on-one like that. So here in this little graphic I put together, we have the Milky Way in its dark matter halo. And then outside of that halo is a smaller galaxy. It's currently forming stars. We call it a field galaxy because even though this galaxy is within its own dark matter halo, it's not nested in any other halo. And so as our little star forming field galaxy is going about its business, orbiting through space, it can be pulled into the Milky Way's dark matter halo through gravitational forces. So literally, we know dark matter interacts with us gravitationally, and it can literally pull galaxies, smaller galaxies, into the Milky Way's dark matter halo. So when a smaller galaxy is inside the dark matter halo of a larger galaxy, that is when it is a satellite galaxy. And I'll talk a little bit about the different things that can happen once a galaxy becomes a satellite galaxy. But right now, just so we have that definition, a satellite is a small galaxy nested inside a larger dark matter halo. And so, as I was saying, we have about 20 to 40, that's a wide range, but we have about 20 to 40 satellite galaxies, so small galaxies around the Milky Way. The vast majority of these were found after 2005, after that digital sky survey revolution, and they are mostly ultra faint dwarfs. So these are my absolute favorite types of galaxies, mainly because we think they are literally fossils of the very first galaxies ever formed. So, think of like way back, there's the Big Bang, stars start, all of this wild stuff starts happening. And the very first galaxies that ever form we think we have some of them living in our galactic backyard. And so it provides this amazing like laboratory to study what happened early in the universe. The one downside with ultra faint dwarf galaxies, aside from their not very creative name, like Dakota had mentioned, is they're not very pretty. So these are literally 3 of our ultra faints, and I promise you there are galaxies in the picture of Tucana 2 and Leo 4. I know it just looks like a bunch of dots on a black background, but I promise, like, Horologium 1 is slightly easier to see. That little kind of cluster of blue and red dots in the center of the image, that is the galaxy. With Tucana 2 and Leo 4, and actually most of the ultra faints, we have to, and we do this for Horologium as well, but we go through this kind of process to figure out if in this collection of stars that you see with Tucana 2, is there actually a galaxy in there? Is there something that we care about? I mean, we care about all stars, but you know, so this is how we do it. And I promise you, this is the only set of really boring black and white plots that I have. So let's get through this. The easiest way to kind of look at stars and figure out whether they have some kind of relationship to one another is if they have similar velocities, because those velocities are kind of, they're tied to the gravitational pull. So if you know that stars are gravitationally bound to each other, you can look at that, how they're gravitationally bound, and determine whether they're living inside a dark matter halo or not. So as you see here on the right-hand plot, which I hope is the same layout for y'all, but the similar velocities, all of the horizontal axis is just the velocity. The vertical axis is just the number of stars with velocities in that little range. And so you can see all of the stars in the galaxy that we're looking at here, which is Ursa Major 1. All of the member stars, all of the stars that we think belong to that galaxy, have a very tight velocity distribution. So they all have similar velocities. And then if you take those same stars and you look at them in literally just like a geographic kind of map, so that's this middle plot where you have right ascension on the horizontal and declination on the vertical. All of those black dots are the stars that have similar velocities. And you can see they form this kind of nice little set of, they fit in this nice little oval. So it's kind of showing again that they're probably gravitationally bound. And the last way, and this is kind of the most critical way, I think, because as you can see with the physical distance, there's a lot of interlopers in there. There's a lot of background galaxies and quasars and stars that aren't members of the galaxies that are kind of messing up the data or the signal. So this last way is critical. We know most galaxies, all galaxies, they kind of fit these standard relations of how bright their stars should be, what chemicals make up those stars. And so the blue and red lines are these kind of standard fits. And this one is so clear. You can see all of the member stars, all of the black circles fall along those 2 lines very nicely. And so these 3 pieces of evidence together are how we figure out that some, you know, funny little image like Tucana 2, which is kind of just a bunch of stars randomly dispersed in the night sky, is actually a galaxy. And so I think, I don't know, in some ways, all dwarf ultra faints are really funny because they don't look like galaxies. There's not much going on, but I want to argue that they're the most exciting galaxies because, one, they're the tiniest galaxies we've ever seen. By looking at their stars' velocities, we can see that they also live in the tiniest dark matter halos that we know about. And even though they're the tiniest and their dark matter halos are the tiniest, the ratio of dark matter to visible matter or to stars is actually the most extreme that we see in the universe. So another way to say that is the proportion of dark matter in an ultra-faint galaxy to visible matter or to stars is really, really extreme. There's way more dark matter in these than there is in any other, proportionally, than in any other universe, which makes them really exciting laboratories to try to figure out what the heck dark matter is, to the point where literally, if we just get a correct count of how many ultrafaints are around the Milky Way, then we can start to put, that would help us put some constraints on the size of a dark matter particle. Literally, from just counting these galaxies, we can help figure out the size of a dark matter particle. Another thing, another kind of way that I think these galaxies are so exciting is that we can tell their stars are ancient, like some of the oldest stars we've ever seen. They're obviously very simple. They're just this little collection of stars. There's no like gas and dust and stuff going on. And so we think that they may be pristine relics from the early universe. But one way that we kind of have to, one thing that we have to get past is, if they're actually relics, if they're actually fossils, then the Milky Way shouldn't have had any impact on them or their star formation history, or how their stars formed. So remember earlier in the talk, I mentioned how a galaxy becomes a satellite. And so this galaxy that we are using as our example, the satellite, came into the Milky Way's dark matter halo, currently forming stars. Within the Milky Way's dark matter halo, there's kind of a lot going on, actually. For example, there's a kind of a sphere or a halo of hot gas and dust. And so if our little satellite galaxy that's forming stars passes through this halo, all of the satellite's star fuel, all of its gas and dust can literally get stripped away by that hot halo. And then pretty soon after that, that satellite galaxy will cease to form any new stars. It'll stop forming new stars, so it'll become a quenched satellite galaxy. With all of our ultrafaints, none of them are forming stars. They are all quenched satellite galaxies. So to be able to know if they are fossils of the first galaxies, we have to make sure that the Milky Way didn't stop their stars from forming. So that's exactly what part of my research has been. So I used this simulation. It's a dark matter only simulation called Elvis. Every single one of these little dots is a dark matter halo. And so what I did was I went in and I found all of the dark matter halos that we think would house our ultra faint satellites. And I looked through to make sure that our ultrafaints have not been in the Milky Way very long. So if they've been inside the Milky Way's dark matter halo for a really long time, that really increases the probability that their stars stopped forming because of our Milky Way's environment. And what I was able to show is that our ultrafaints didn't spend that much time within the Milky Way's dark matter halo. They've only come close to us more recently. And so that means that they are actually fossils of the very first galaxies ever formed, which we can then go on to answer all kinds of exciting questions. And one of the next questions that I'm answering, I'm using a kind of a next generation dark matter only cosmological simulation. So again, just a dark matter simulation of the Milky Way and our satellites. But this one has this kind of augmented gravity in it that gets closer to the number of satellites and ultra-faint dwarf galaxies that we see around the Milky Way. So we think it's a little more accurate with this kind of additional gravity put inside of it. And so what I'm doing is literally comparing our simulations to our observations that we see through the Gaia Space Telescope. Gaia is this amazing telescope that has given us full velocity and position information for like 60 of the little blobs and things and satellites and galaxies around the Milky Way. And so I can compare observations and simulations and kind of back out the mass of the Milky Way. And this is why I love galaxies so much, because you can use them and study them to answer everything from what the heck is dark matter to what happened in the very early universe, even the kind of big fundamental questions like how big is the Milky Way actually? So that's my talk. Thank you all for listening, and I will take questions now, but let me find the chat box. Here it is. Okay. Oh, there are questions. Awesome. Where the satellite galaxies thrown out of the Milky Way in its evolution? If so, in what stage? So satellite galaxies can be thrown out of the Milky Way. This kind of happens fairly often, actually. So let's see if I can go back. So this picture, yeah. So if you see in this picture, you can kind of get it, but galaxies are on their own orbit, or satellite galaxies, you know, they have their own orbit and they interact with other satellite galaxies as well. So there are some times, and we think it's possible that some of the ultrafaints that we do see, like Eridanus 2 is like this, that Eridanus 2 probably came in really close to the Milky Way, similar to this last image here. But then it got shot out. And so right now, we believe it's just outside of the Milky Way's dark matter halo, but that there's a chance it probably was a satellite at one point in time. And that doesn't entirely have anything to do with the evolution of the Milky Way. I think it's a little more has to do with just the different orbits that the satellites get into. Okay, so how does the size of the Milky Way galaxy compare to other galaxies? Is it larger, smaller, or somewhere in the middle? That's awesome. So it's actually kind of somewhere in the middle. Galaxy-wise, we're kind of just, yeah, we're basically floating around in the middle of, there's galaxies that are way more massive than us, and obviously with the ultrafaints that are much, much tinier than us. So we're kind of middle of the road, which in some ways, I guess can be boring, but in many ways it's really exciting, because if we are what many galaxies and many systems in the universe look like, then we can study what's happening close to us and be able to kind of infer what's happening out in the rest of the universe where we can't get as deep of data yet. And okay, these are great questions. Thank you. How are you confirming that the satellite galaxies are newcomers to the Milky Way dark matter halo? So we confirm that pretty much only through the simulations right now. It's really hard. I don't know if there's any observational way to tell whether a galaxy has been near us for a long time or not. Obviously, galaxies that are closer, or yeah, that are much closer to the Milky Way have been in the Milky Way for a while, because, you know, they had to get close to us. But the galaxies that are further away, we don't quite have that information just through observations. So that's why we use simulations. And there's a lot of very detailed stuff with figuring out what dark matter halos we think house our satellite galaxies that we do observe. But then simulations, it's really easy to, if I say, you know, if I label one dark matter halo and say this one houses Tucana 2, I can track it from the beginning of the universe to the beginning of that simulation all the way to today, and just literally find out, like, at what point in time did that halo cross over into the Milky Way's dark matter halo. And about how old is the oldest star that's been observed in a satellite galaxy? About 13 billion years old. So literally, some of these, especially in the ultrafaint, some of these stars are probably the first stars, some of the first stars that were ever created, and then became part of the first galaxies that were ever created. And I think that's it for questions. I think I got them all. Okay. Thank you.
Thank you so much, Katie. Once again, that was an absolutely fantastic talk, and we really appreciate having you here as part of our event today as well. And then next up, we have our last phase of today's event. Isabella and I are going to briefly talk about some exciting recent astronomy news, and then we'll have our trivia contest at the end.
Yeah, so first up is actually some rather sad news, but we actually lost a telescope fairly recently. So the Arecibo telescope was a big radio telescope in Puerto Rico. And a couple months ago, a lot of its important components sort of started falling apart. But I wanted to take today to talk a little bit about the history of the telescope and some of its big achievements while it was around. So on the right is a picture of Arecibo. It was built in 1963. And it has a pretty unique construction. So it's in Puerto Rico, and they sort of fit it into this natural sinkhole that was already in the landscape to accommodate the dish and stuff. So it's an enormous telescope. There's a little building up here, if you guys can see, for scale. So it's about 300 meters in diameter. And when it was built in 1963, up through a few years ago, it was the largest single dish telescope in the world. It doesn't quite look like what you usually picture when you think of a telescope, but it does have all of the same general components. So it's got this really big dish on the ground here that will kind of collect all of your light. And then it has this cool platform that's suspended above the dish that has all of the instruments and receivers. So if you've got some signals that are coming from space, they'll come bounce off your dish and they'll be fed into that little white dome that you see there. So this was what Arecibo looked like, and over the years, it was able to do a lot of really cool science. So it was looking in the radio, and these are just like a few of the first that it was able to do during its life. So one of the things it was great at was finding pulsars. So these are like really compact stars that are spinning pretty quickly. So it could find a lot of these, and it found a lot of special cases as well. So it saw some that were like pairs of pulsars that were inspiraling. And that was pretty cool because it was like really early evidence for gravitational waves before things like LIGO and stuff really picked up those types of experiments. Arecibo also was able to make the first exoplanet discovery, an exoplanet around a pulsar as it happens. So that was pretty neat as well. And it's did a lot of like mapping of different surfaces. So it looks at Mars, at Venus. It told us a lot about the shapes and surfaces of near Earth asteroids. And then a kind of fun thing that it was famous for was that Arecibo can not only like take in light, it can also emit radio waves. And so it sent a message to a nearby star cluster with a bunch of different information about Earth. So it actually had like a little self-portrait of Arecibo on the right here. It had pictures like of DNA and what did the double helix look like. It told people about how tall a human being was. All of this kind of information being sent out. So it was doing all of this science for decades. And then a couple months ago, all of that kind of came crashing down. The reason for this, people think, was that for a while, Puerto Rico had faced a lot of natural disasters. There were hurricanes and earthquakes. So we think that plus some natural wear and tear on the telescope started to sort of wear things down. So in August of last year, one of the cables between these big towers broke. And as you can see in the picture, because all of our instruments are suspended in the air by these cables, the cables are fairly important to the structural integrity of this whole thing. So when that cable broke, the telescope was sort of okay for a little bit. Later in November, a second cable broke. And then very soon after that, the whole thing kind of fell into the dish, which is the picture on the right. So that sort of marked the end of the observing with this telescope. But to leave it on a not too sad note, there are different ideas for what might come next with this. On the right actually is a fairly recent picture, I think from earlier this week, where they're starting to just sort of clean up and dismantle the current telescope. There are some ideas floating around about putting new facilities in, maybe a new radio telescope. Whether or not it'll look like this at all is really up in the air. But it'd be a really long time before people agree on exactly what sort of design that would be or where the funding would come from to do that. But it's still a possibility. And in the meantime, there are still actually a few different instruments at like around this area that aren't associated with the dish. So they are still doing some science there in the meantime. So all is not lost. All right. And up next, Pratik has some more tearful news about Mars and the Perseverance rovers.
Awesome. Thanks, Isabella. Before I go on and talk about Mars, I just want to recognize that I made a mistake earlier. After the first talk, I accidentally thanked Dakota and Katie. It was supposed to be Dakota and Lisbeth who gave the first talk, and then Katie gave our second talk. So sorry for causing any confusion in that regard. But moving on to the Perseverance rover, pretty much over the last month or so, if you've been even remotely near the news, you've probably heard a lot about the Perseverance rover, which just touched down on Mars on the 18th of February and represents the 5th of NASA's rovers to be on the Martian surface now. So throughout human history, there have only been 5 rovers sent to Mars, all of them by NASA, and this kind of represents the latest and greatest of them. And there's a lot to talk about Perseverance. There's a lot of really cool science and really interesting design features, but its main goal is to examine the surface of Mars for signs of extraterrestrial life. And so it's going to collect a bunch of rock samples. And the really cool part is that it's actually going to conduct some preliminary studies on those samples. And the super interesting ones, it's going to leave at specifically designated points on the Martian surface, which will then be collected by future missions that are sent to Mars. And that kind of just blows my mind that we're planning to just keep those samples lying around on the Martian surface and sending another mission at some point to collect those. I think that's super cool. And I already mentioned that we've kind of had 5 Mars rovers sent to Mars. So this is an image of a decal, a sticker that was put on Perseverance, and it kind of represents its family tree. It shows the evolution of all of Mars rovers through the ages. So this first one highlighted here, the really teeny tiny one, was the Sojourner rover sent in 1997. Then you had the Spirit and Opportunity twin rovers sent in 2003 or 2004. And then many of you might remember the Curiosity rover that was sent in 2010. And then finally, now we have Perseverance. So you can, I thought this decal is really cool. It kind of shows you how they've changed through the years. And I personally wasn't able to catch the Curiosity landing back in 2010. So I was really happy to be able to catch the Perseverance landing earlier this month. And like I mentioned, there's a ton of things we could say about Perseverance. I thought we could just, in the short time we have, do it justice by highlighting some of the really cool images it's taken during its time on the Martian surface so far. So this first one is just the first color composite image to be sent back to Earth by Perseverance. And it's its first color view of the Martian surface. And there's some really cool geological features that you can see in this one. Next up, we have, sorry, I guess that part of the slide has some kind of issue. But next up, we have this panorama of the Martian surface that was taken by Perseverance. It actually just took a bunch of pictures, and then they were all stitched together once those pictures were sent to Earth. And again, I just think it provides a really cool bird's eye view of the Martian surface and a lot of the interesting features on it. This shot was actually taken while the spacecraft carrying Perseverance was crashing through the Martian atmosphere on its way down to the surface. And it was taken right after the parachute opened up to slow it down. And the really cool thing about this parachute is that in this pattern of white and red colors, NASA engineers have encoded a secret message, and that secret message says, "Dare mighty things." And that's basically like the NASA JPL motto of sorts. And then finally, we have this image of Perseverance, the rover, being lowered down from the spacecraft that was carrying it using what's called a sky crane. And this is honestly probably the coolest part of the mission for me. The spacecraft carrying the rover essentially just hovered above the surface using its thrusters, and then gently lowered the rover all the way down using these umbilical cords, after which the cords were severed, and then Perseverance could be on its way. And I think that's absolutely wicked that we can do that. And then lastly, one of the other super cool things about this rover is that it's actually carrying a helicopter. And in a few days, at some point when they find a suitable site to perform this test, we're probably going to have the first ever helicopter flight on Mars. And that's also something that's just absolutely wild. The helicopter that the rover is carrying is called Ingenuity. And I believe its mission is to just be like a proof of concept prototype test to see whether it's actually possible for us to design helicopters that can fly in the thin Martian atmosphere. And based on how Ingenuity fares, we can then start planning for further, more complicated aerial vehicles on Mars. And so this was just an all too short selection of highlights from recent Perseverance images. If you're interested in learning more about it, NASA has some really cool infographics and some really cool animations all over their website. So please do go check them out. And then finally, for the last part of our evening, Isabella is going to introduce us to the rules for our trivia contest with lots of prizes to be won.
All right, so we've got trivia up next. There are not many rules. We've got 8 questions for all of you. And if you've got a sheet of paper or anything at home, go ahead and just write down your answers. It's all on our system today. We're gonna roll through the questions a few times. So if you need to stretch, get a drink of water, say hi to a pet, feel free to do any of that. And we'll come back on in about 10 minutes and share the answers with everyone. All right.
Great, so I'm gonna start showing the trivia questions now, and I'll keep changing them after 20 seconds or so. Hey, everybody, we're just going to cycle through the questions one more time. And as was mentioned in the chat, make sure you take a picture of whatever you've written down, and then we'll tell you how you can get your picture to us if you've gotten the answers right to claim a prize. Okay, hopefully that was enough time for everyone to at least take a stab at answering the trivia questions. On the left here, we have a list of the correct answers for all of them. So compare those to the ones you've written down. And if you feel confident that you've gotten at least 6 or more correct answers, please send us an email at any one of these email addresses with a picture of your answers. And then we have like 3 to 5 different prizes to give out. So depending on how many people get a lot of answers correct, we'll enter your names for to be in the running for a prize. And once you send us a picture with your answers, we'll contact you about prizes and which one you want to choose afterwards.
All right, so before we take off for the evening, I wanted to thank all of our speakers, organizers, and all of you, our guests, for joining us. So Elizabeth, Dakota, and Katie, you guys gave awesome talks. Thanks so much for volunteering your time tonight. And I wanted to thank Sanaya, Patty, and Isabel as well, who helped us plan this event. So thanks everyone, and enjoy your evenings.
And lastly, make sure to follow both Astronomy on Tap West LA and Astronomy on Tap Davis if you like this event. And if you aren't already following us, you can also email us at any point to learn more about our programming. We're not sure when in the future we'll have a joint event again, but we'll definitely be continuing with other virtual programming in future months. So yeah, thanks everyone for attending. We'll end here today and we'll leave these slides up for a bit.